CIFAR-10 so far.
Awesome. Okay. So this is a talk on my paper called 94% on CIFAR-10 in 3.29 seconds. So CIFAR-10 is a data set containing 50,000 32 by 32 color images. It's a classification data set. And I think it's the most, I believe it's the most popular data set in machine learning at this point with 14,000 papers. At least on papers with code, ImageNet is like 13,000. So it should be either like the most popular data set or the second most popular data set. Personally, I enjoy doing a lot of research with CIFAR-10. But when I don't have any GPUs, like especially if I have a weaker GPU or if I don't have a lot to run multiple experiments, then a lot of my time ends up being spent just waiting for training to finish. So with this project, I wanted to try to build a really fast training configuration so I can run lots of experiments quickly. So my goal is to reach 94% accuracy. Well, so I sort of just I picked some goal for myself to try to iterate and make a faster training. So the goal I picked is to reach 94% accuracy in the shortest possible time with fixed hardware. So not by scaling hardware. Like, of course, you can sort of always make training faster by using multiple GPUs or like a better GPU. But I wanted to do a fixed hardware. So it'll be 94% accuracy on a single NVIDIA A100. And the 94% target is somewhat arbitrary, but it seems like the nicest target because previous speed records used it. And also Andrej Karpathy says in this like blog from 2011, he says this is his human level accuracy. So he tried to classify some images from CIFAR-10 and found that he got about 94%. Okay, so the baseline, the best previous time for this task on the same hardware is this repository called Hyperlightspeed Bench, which is what I'm starting from, and it's a great repository. And it reaches 94% in 6.3 seconds. I could theoretically describe the difference between this training and mine, but that's kind of complicated. Like there's a lot of small differences. So I think it's probably better to just explain my training from scratch. Okay, so the first thing is the network architecture. And yeah, so I'll just be talking about the training basically. Like for the rest of the talk, I'm going to be just talking about the methods that I use to make the training fast and just everything that goes into the final training. So the architecture that I'm using is the following. This is the entire description of the architecture. So if anyone reads, and I'll sort of describe it in English too, but if you can read PyTorch, honestly, you might want to like ignore what I'm saying and read the code. But so yeah, so this is the architecture. The basic convolution is it's very much like a VGG architecture. There's no residual connections. And this is based on iteration. Like I didn't design this with any goal of like I want the architecture to look a certain way. I just iterated experiments until finding the best possible thing. So this is kind of resulting from my own like evolutionary almost algorithm of like I think I ran something like 800 experiments to get the final training configuration, many of those being architecture evaluations. So this is kind of the result of that evolutionary process of just trying to get a better architecture. And it's largely based on the previous record. So I only changed a few things, but I tried to change a lot more. So I tried all sorts of things. And this is really just what works the best. So yeah, there's no residual connections. It's composed entirely of 3x3 convolutions and I don't use a bias, so no bias, and batch norm layers and the GALU activation, which is similar to the ReLU, but there's a slight like it's sort of it's differentiable at all points. So there's no first order discontinuity, and then it's a little bit negative in the negatives. So yeah, so the basic convolution is the 3x3, but then the one important difference is the stem is a 2x2 convolution. So, and that'll come into play in the next slide. And yeah, I mean, even these n dot sequentials in the middle here can be removed, and you just end up with, it's literally just a sequence of conv, max pool, batch norm, and the activation. So by baseline training this with an SGD Nesterov, so basically just SGD with batch norm 1024 and some basic data augmentations, if you end up training that for 45 epochs, you get 94%, and that takes 18.3 seconds. So the single most impactful method for this training, for training on CIFAR-10, is to initialize the first convolution using what's called a patch whitening initialization. And that, the whole initialization you can see right here. So it's a 2x2 convolution with 24 filters, and you initialize it to these 24 filters. And that ends up more than having the training time, so that it takes only 8 seconds to reach 94%. So how do you compute these filters? So these filters they're the directions of independent variation for the patches of the image. Which means if you just collect like patches that you would be feeding into the convolution, if you collect like 1 million of them from the images, and then you ask, what are the directions of independent variation for these? So like if you do a singular value, well, I guess there'd be multiple ways to do it, but if you do an eigendecomposition of the correlation matrix at the patch level, then these are the directions you get. So yeah, each of these directions varies kind of independently, and it looks kind of interpretable. But yeah, surprisingly, just that alone, it doubles training speed. I guess the network ends up spending like half its energy just trying to figure out the right first layer. The next most sort of impactful architectural change is something called that. There's a lot of names for it, but I would call it identity initialization. So residual connections, if you kind of think about what they're doing, they are they kind of bias each layer or each like block towards the identity. Meaning, let's say your weights are 0 and you just like the convolutional weights are all 0. So it's just the identity connection that's doing all the work, or the residual connection. Then you get the same thing out of the block that you got put into it. So you can sort of do a similar thing to like single layers. You can just initialize them a convolutional layer so that it's computing an identity. And there's a torch function that does this, called init.dirac. And so what it's doing is if you have a 3x3 convolution, it's saying I just want the middle weight to be 1 and everything else to be 0. And if it's passing over multiple channels, then I just want the channel corresponding to the output channel to have that 1 weight. So there's just going to be 1 weight in the entire filter for each convolutional filter, that's 1, and the rest of them are going to be 0. So if you initialize, so you can't do a perfect identity initialization when the layer is increasing the number of filters. So you just identity initialize the filters, like the first n filters. If you're going from n to m, where m is more than n, you identity initialize the first n. And that ends up saving, I suppose, 1.2 seconds. So you get down to 6.8 seconds. So it saves like, I don't know what that'd be, but quite helpful. And yeah, so the hypothesis would be similar to residual connection. This is going to help with your gradient propagation. But of course, it's empirical. You just try it, and it works. Okay, so the next method I used is several optimization tricks. And these are descending from previous speed records that found that these worked. The first one being to increase the learning rate for the batch norm biases. So all the batch norm layers, they're doing batch normalization, so they're sort of normalizing their input, and then they have both a bias, and then in this case we disable the weight, so there's just a bias. They're just adding to all the outputs to the batch norm. There's a bias being added. to each of the channels. And if you increase the learning rate for these biases by 64 times, so this huge increase, it ends up saving a lot of time. So it goes from 6.8 to 5.1 seconds. That's like a huge time save. And I did some interpretability in terms of looking at why this is so helpful. It turns out that it really just is that the old learning rate is too small. Like if you look at with the learning rate that's optimal globally, if you look at the trajectory of the batch norm biases, they're just very slowly getting to their optimal value, much more, whereas everything else is sort of oscillating. So you really just need a larger learning rate for the batch norm biases. Yeah. So, and then the next thing is using look-ahead optimization. And look-ahead is this very interesting, it's really a wrapper for any optimizer. And what it does is instead of you just repeatedly normally you just take steps according to the optimizer. And then the optimizer has some internal state. Like with Atom, you would have, the momentum and the second order internal state. And then for SGD, SGROV, you would just have the internal momentum. Look ahead is just a wrapper for anything. So you could have like a look ahead Atom. But what it does is it adds a second state where it says you're going to take normally 5 steps with the inner optimizer in whatever direction. And then you're going to move from, and then you're going to have, so how would I say it? So you start at some position, then you take 5 steps with using your inner optimizer, and then you interpolate between where you started and where you ended up with the inner optimizer. And for some reason, this is helpful. I don't really know why, but for some reason, it's helpful. It's helpful on ImageNet. It's helpful on CIFAR-10. Honestly, I wonder if there's like a bunch of optimizer competitions coming up, and I wonder if it'll win. We'll see. It'll be very interesting. But adding that saves a little bit more time. Okay, then one more method is test time augmentation. So for ImageNet trainings, for these kind of series of papers that came out between like 2012 and 2017 on improving the ImageNet state of the art, one of the factors, especially early on, was using better test time augmentation. What that means is this doesn't improve the quality of the trained network, but it improves the way you do inference with the trained network. It's kind of like with language models, how you use like a better prompt to get a better result. For these old ImageNet trainings, you would use more and better test time augmentation to get a better result from the same model. And the classic method of doing that was you would feed multiple props to the same model. So you'd say, okay, I have my trained classifier. Now I'm going to take an ImageNet image and I'm going to feed many different props from the image and collect all the different predictions for each of those crops, and then predict using the average of that output. And so these trainings ended up, I think the AlexNet training, well, it definitely didn't use a lot of crops. Anyway, it definitely didn't use many crops. And then soon, by like a few iterations later, they were using 144 crops or something like that. So there's this huge inference time cost. For my purposes with training speed here, I'm including the inference time in the time. So I can't use an infinite number of crops. And it turns out the balance is to use 3 crops and horizontal flipping test time augmentation. So I'm trying to do this. Yeah, so I would use 3 crops where one is up and to the left, one is down and to the right, and they're all flipping. So you get 6 total inputs to the image. You have the center, the up and to the left, down to the right, and both back and forth for each one. And that saves a bit more time. It saves 0.4, adding those 3 crops saves another 0.4 seconds. And we're now much past the previous record. Okay, now a lot of what's been going on before is really kind of just tuning or optimizing the previous records. Like everything else before now there's been nothing like really too fundamentally new. Like it's kind of just optimizing. This one method now is probably the most novel thing that I used. So it's a method called alternating flip. I'll begin with motivation for it. So the textbook definition of stochastic gradient descent, or SGD, it actually, the way we train neural networks in practice is different than if you would read a textbook on how SGD works. So in a textbook, SGD says, just repeatedly feed the network with IID batches of data. So there's no notion of epochs. It just says every iteration collect from the data set your IID batch, which means that you might have two batches in a row that contain some similar images. There's no notion of like an epoch. So yeah. But we don't do that. We instead sample without replacement, whereas IID is with replacement. So we say, once you sample a batch of data from the training set, batch of examples, don't ever sample that again until you run out of the data. You run out of data, and then you start a new epoch, and you start again. And why do we do that? I mean, and you can test that if you don't do that, it's much worse. You get a much worse result. Training is significantly slower if you do IID. It's not. I think ultimately it converges to a similar thing. Well, is that even true? No, that's not true. Sorry. It's just worse. If you do IID sampling, you get a worse result. And so, of course, that's just empirical. But if you think about why might it be worse to do it with replacement sampling, I think it makes sense to say, if you sample multiple times and you get similar data each time, you're kind of wasting uniqueness. Like you're not really maximizing the diversity of the data that you're training with. Like if in any, well, the way the math works out is like if you have a training set of n examples, and you sample n examples IID, then you end up only getting 1 minus 1 over E of all the examples sampled at least once. And then many of them are sampled multiple times, but then 1 over E of them are never sampled, which is about like 30%. Maybe it's more, it's like 37%. So you're wasting like 37% of your kind of examples. They're just unique things they're non-unique things you've already seen this in the last n examples. Okay. So that's true for sampling which example you sample. But we're also doing this random augmentation. And for this training, the most impactful augmentation that we use is random horizontal flipping. If you turn random horizontal flipping off, that's like the most common augmentation in computer vision, if you turn it off, you get significantly worse accuracy. I mean, we'd be nowhere near 94%. And when I think about what horizontal flipping is doing, there's a similar. It's by default we're doing it in an IID manner, where every time you get a particular example, you just randomly choose whether to flip it or not. But here's kind of the motivating observation. If you do random horizontal flipping normally, IID, then every 2 epochs, you don't actually see all possible flips. Meaning, let's say you have no other augmentations besides horizontal flipping, you just flip. And that means that if you have n examples in your training set, then there are 2n unique possible training examples because there's just every example in its flipped counterpart. And so if you do flipping as normal, well, in 2 epochs, then half of your images are going to be flipped the same way both times. And then half are going to be flipped both ways. So half are going to have like they're going to be seen 2 different ways, whether it's not flip, flip, or flip, not flip. So overall, you're only going to get 75% of all possible unique inputs to training. So it's again the situation where like what would happen if you sample IID examples. If you do IID flipping, you get 75% of the unique possibilities. So you're kind of wasting uniqueness. So the idea is just let's try to enforce that we get 100%. So let's say every 2 epochs has to have both flips. And this will be probably easier with a picture. So the left and I guess we have to look, kind of takes looking a bit closely here, but like the left is normal random flipping. So we can see there's situations where like for the last three, you probably can't, I don't think you can see my mouse, but like for the last three epochs out of these five here, this represents 5 epochs in each case. So it's how 8 examples are seen during 5 consecutive epochs. And if you do random flipping, you get these situations where like many epochs in a row, you get the same flip. And it'll be moved around a little bit by the random cropping, but it's the same flip. So it's sort of, yeah, so it's the same flip. And this happens many times, like half the images are the same in any 2 epochs. So alternating flips just says, let's just flip everything every epoch. So the first epoch, you flip half of everything. And then after that, it just alternates between epochs. So it ends up sort of fixing the situation where you have potentially repeated flips. Okay. So yeah, that's the definition. The result is, yeah, it just works. Like if you use alternating flip, the training time gets reduced from 4.2 to 3.83 seconds. And the way we've been reducing training time this whole time is by every time we add one of these new features, one of these new methods to training. I've been reporting the time as like, I reduce the epoch count until the level that it gets 94%. Whereas now that we've added all these features, if we still used 45 epochs, like in the beginning, we'd be getting like 94.7%. So adding these series of features has allowed us to reduce the number of epochs to turns out 9.9. And it's fractional, meaning for the last epoch, you only do 90% of the iterations of that epoch. Yeah, and so yeah, once with all these features, then you get down to 3.83 seconds, and it takes 9.9 epochs. Yeah, which is not the final time of 3.29 seconds. To get that, we add the very last feature, which is not actually, it doesn't change sort of the mathematical definition of our training. Like you'll get the same exact distribution of outputs. So it's torch.compile. It's just a nice feature from Torch that it just speeds everything up. And I'm not above anything. I'll use anything to speed it up. So that speeds it up by 14%. And that's the final time, 3.29 seconds. So at the end of the day, that's 1.9x faster than the previous record, which was 6.3 seconds on the same hardware. And as kind of a matter of a historical note, it's actually, I used a flop counting tool to count the number of floating point operations of the training. And it turns out it's 26 times less flops than what was the state of the art in 2011. So the state of the art in 2011, it was a convolutional network training. And it used 26x more flops and it attained 80.5% accuracy. That was actually a Schmidhuber paper. And that was the state of the art in 2011. Which was the year before kind of the AlexNet moment happened. So the progress from 2011, people talk about like, progress is entirely based on, a lot of it is based on scaling up hardware. Apparently there actually has been algorithmic progress. So the training I have here, like part of the speed is what I put into it, and then most of it is what previous people like got with the previous record. Like a lot of these techniques are from the previous record. So it's kind of a series of algorithmic developments, of course. And yeah, it's just the algorithmic progress actually has allowed us to, on this task, which was like the most studied task, just continually reduce the amount of computation you need to get a certain level of accuracy. Okay. Okay, now I'll look at, so that basically gives you, I certainly am omitting some like details here, and I'd be happy to answer any questions, but those are the main, like, that's the main features that go into the training. That's the description of the training. And by the way, the training it's released as a like 481 line PyTorch program. So it should be readable if anyone feels interested in reading it. To really get 100% of the detail. Yeah. So, okay, now I'll look at some questions we might ask once we get this result. The first question is, did we end up overfitting CIFAR-10? So while I developed this training with just this iterative experiments, I didn't look at any other data set. I just said, I just want to get the best time on CIFAR-10 possible. I'm just interested in CIFAR-10 research. Like I plan to do, more papers on CIFAR-10, more experiments on CIFAR-10 in the future. I just want a fast CIFAR-10 training. So yeah, so potentially I overfit to CIFAR-10, right? Like potentially, maybe this training now only works on CIFAR-10. Well, let's find out. So I'm going to compare to a standard resident 18 training as the baseline. And I'm going to compare that to a variant of my training, which reaches 96%. So it's like it's somewhat a souped up training. It's the exact same thing I just described, except you increase the size of the network a bit and you increase the training duration, and you use cutout augmentation. So you're kind of increasing the data and the model size, just like sort of typical scaling, because you're training for longer with more augmentation. And that scaled up training, which takes about 40 seconds. That gets about the same level of accuracy as a Resident 18 training on CIFAR-10, which for comparison takes about between 4 and 7 minutes or longer, depending on a lot of things. But it's comparable in accuracy on CIFAR-10 to a Resident 18 training. So yeah, so with cutout, they both get about 96%. Without cutout, they get about 95.5 to 95.6. So the question will now be, what happens if we do a different data set? Does what's called the air bench, which is like, that's the name that I gave to this training, does that just collapse? Does that just fall apart? Is it completely overfit to CIFAR-10? Well, let's see. Okay, so yeah, the answer is it turns out to not be overfit at all, even though I tried to overfit it, to be honest. I mean, I tried to just make it go on CIFAR-10. So on CIFAR-100, it actually does better, weirdly. Like it gets almost 1.5% better in both the with cutout and without cutout configuration. Cutout is another data augmentation. That's useful for these larger trainings. So both with and without cutout, it gets about 1.5% better than the Resident 18 training. And then the other data sets, for the other data sets, it's just the same. Like for a Cynic 10, it looks like a pretty similar, maybe slightly better. And for SVHN, it's again slightly better. And these are other like common benchmarks. So yeah, it turns out that even if you do your best to overfit a training to one data set, it does not overfit. It just still gets better in everything. Like in terms of, I mean, of course, you can't evaluate the model that you train on these other data sets. That won't be good. But the training itself, you can't really overfit it, apparently. Yep. Yeah, that's all I have to say about that. So let's see. Okay, so another question is, and this is the next question. Then after this, my talk will be pretty much over. We can go to questions. Does alternating flip generalize to ImageNet? So we have this new method. Just let's see if it generalizes to ImageNet. The first thing that's necessary to understand about ImageNet is that it uses a much more aggressive random resized crop augmentation. Random resized crop being the way you train an ImageNet is you pick a patch within the training image, and it's a random patch. It's a random sized patch, and then you either blow that up or shrink it to become the training input. And then people typically do it with a very aggressive strategy. So you're picking it can sometimes be even just 8% of the input of the actual training image. So you're picking like a random 8% rectangle, and then you're turning it into the training input. And you're saying predict the label, like predict which dog breed this is or whatever from this just little 8% patch. Anyway, so that's sort of one of the most salient facts about ImageNet training. So okay, so let's test whether alternating flip helps both with and without this random resized cropping. So we'll do it for ImageNet trainings that both have random resized crop and then ones that have a much like weaker crop that's similar to the CIFAR-10 case. Okay, so first, when you don't have this aggressive resized cropping, Yeah, it helps. Without the resize, without this aggressive cropping, alternating flip, it just helps. It increases accuracy by about 0.3, 0.4% on ImageNet, which is considered fairly significant. And this is equivalent to, if you look at it as a function of like how long you train, it can save you, 25%. Which is fairly similar to what you see on CIFAR. It's actually a little better than what you see on CIFAR-10. Okay. But when you add this random resize cropping, this really aggressive like 8% cropping, it turns out that flipping, not only does alternating flip not help over random flipping, but it turns out that apparently random flipping itself is not even much better or better at all than no flipping, which was really surprising to me because I thought, this is like the augmentation that everyone always does. And it turns out it doesn't even help in this case. Now, if you train for much longer, like I'm doing a relatively short training, if you train for much longer, it starts helping a little bit, but it's not very helpful. Whereas, of course, if you remove the random resize cropping, it's going to be terrible. So it's like, that's not very impactful, but the flipping is just not very helpful at all. So yeah, so it doesn't help. It doesn't help in that case, sadly. Yeah, I think that's all the question. Yeah, those are the two questions that I asked. Yeah, that's the end of my talk. Thank you for attending. I appreciate it. And yeah, are there any questions anyone has?
Thank you so much for your talk. Let me stop the recording.